on.
Okay, thank you very much for the invitation. So I changed a bit my title. I wanted to talk also about continuum directed polymer, and then I realized it would be too much. And finally, I looked back at the theme of the session, and I realized that it had nothing to do with stochastic partial differential equation. So I wanted to have this connection with a directed polymer. And okay, I'm also very grateful to Renato for doing this talk before me, because I think it will help me a lot when I try to explain things, because it has the same flavor of localization phenomenon. And this work is joined with Quentin Berger from Paris and with Karsten Chong from Columbia University. Okay, so what I will do first is a very short and incomplete survey on directed polymer in random environment, and I will kind of highlight the results that have a connection with our work on the stochastic heat equation. Okay, I'm talking about I will investigate the stochastic heat equation with multiplicative Levy noise. So I think before that, it would be good to discuss a bit what has been done in the Gaussian case, but this will have to be very short as well. Okay, so let's go. So what is directed polymer in a random environment? Well, it's a kind of version of the parabolic Anderson model, but in discrete time, and where at each time you're allowed well, you're changing the environment and you're taking IID environment at each time step. And it's a model that can be thought as being something to model the behavior of a polymer chain in a medium that has impurities, and well, the chain will interact in a different manner with each impurities, and you want to know if this affects the spatial configuration of the polymer. Okay, so what is the mathematical definition of the model, or how do we model this polymer? So the polymer is modeled by the graph of the nearest neighbor path in ZD. So the fact that the polymer is not a path in ZD, but the graph of a path, means that somehow it cannot intersect itself, and you kind of throw away already all the kind of problems you would have with self-intersection, which is okay, a way to simplify things. And the environment is modelized by well, IID random variables that are indexed by, well, n times ZD, because you have this other direction, which is the time direction. Okay, and our directed polymer model is a probability measure that gives different weights to this n-step path. And well, the way you define the weight of a path is, well, you simply take a weight 1 plus beta eta for each space-time site that the graph of the path visits, and you multiply it over every path, over every site. Okay, so okay, here what is beta? Beta is just a parameter that kind of modulates it's kind of the amplitude of your disorder. Okay, I consider beta smaller than 1 because I've taken the assumption that eta is larger than -1, and this makes this thing positive. So there is nothing very special in our assumptions, and I assume that my environment has 0 mean for practical reason as well. Okay, so in fact, I'm saying that the polymer measure is a measure on n-step path. It's more convenient to say that it's a measure on infinite path, and then for you will only check the distribution on the first n steps. And a way to say again what I've said on the previous slide is to say that the Radon-Nikodym derivative of the polymer measure with respect to that of the simple random walk is proportional to this functional that I introduced before, this product over all space-time sites visited of 1 plus beta eta. And if I want to make this a probability density, I have to renormalize so that the expectation is equal to 1. And this Zn, which I call the partition function, is this renormalization factor. So if you've already seen talks about directed polymer, it's really probable that you have not seen the weights, the Gibbs weight in this form, that you have seen things in the exponential form. Instead of having this product, you had the exponential of a sum of beta etas. Well, if beta is fixed, really, what you're doing really is just a change of variable here. So it's not very important. But this presentation is a bit more convenient for my talk today. So this is the reason why I adopted this. Okay. So what people have been interested in the study of directed polymer is the issue of path localization. So they want to know if, well, they want to know under the polymer measure how the typical distribution of paths behave. And it turns out that this really depends on one crucial factor, which is how Z compares to its expectation. And with my setup, the expectation of Z is simply equal to 1. And there are two regimes that are relatively well understood. The first one is the weak disorder regime, which is actually very well understood. And it is said that weak disorder holds when the partition function converges to a positive limit when n goes to infinity. So in particular, this means that Zn typically behave as the same order of magnitude as is its expectation in the limit. And in that case, the trajectories under the polymer measure are diffusive. And in fact, you can even prove a full invariance principle, so convergence to Brownian motion. And okay, the study of this regime started in the 80s. And well, the proof of the invariance principle is due to Komets and Yoshida in 2006. The other regime which is understood is the regime of very strong disorder. And we say that very strong disorder holds when, well, not only the partition function tends to 0, but it tends to 0 exponentially fast. So the log Zn, when divided by n, converges to a negative limit. And in that case, you have a phenomenon of localization of the trajectories. And okay, there are still things to understand in that regime, and it's an active field of research. But okay, basically, what is known in that case is that if you look at the distribution of the endpoint of the polymer, this is something which is localized on a finite number of islands of finite diameter, to have the terminology of to use the terminology of Renato, and this was proved by Chatterjee and Bates quite recently. And basically, what is believed is that these two regimes are the only ones that exist. But what is known is only that well, there are two critical values of beta C and beta bar C, and that below beta C you have weak disorder, and above beta bar C you have very strong disorder. But people cannot exclude that there is a regime in between in which neither of the two holds. Okay, so this is a big conjecture in the domain, is that these two things are equal, but this is still open. Okay, so in fact, this is not all the story, because whether you have a weak disorder regime really depends on the dimension. And I will tell you what's the story of this when your environment has finite second moment. And in that case, it was proved that well, there is a weak disorder regime when d is larger than 3, so that when beta is small, trajectories are diffusive, and this was proved in the 80s by Imbrie and Spencer and Bolthausen. And on the contrary, when d equal 1 or d equal 2, you have very strong disorder for every beta. So you don't see this phase transition when in dimension 1 and 2. And in fact, you can even characterize how fast the partition function decays to 0 in the limit when beta goes to 0 in dimension 1 and 2. In dimension 1, this exponent, okay, this p beta, that is the rate of convergence to 0, behaves like beta to the 4, and the exact constant was identified by Nakashima recently. And in dimension 2, p beta goes to 0 when beta goes to 0, but in a much slower fashion, which is exponential minus p over beta square. And this kind of behavior, the fact that you do not have a power of beta in dimension 2, kind of underline that dimension 2 is critical for the directed polymer model. And of course, these things are only under the assumption of second moment. The results are completely different when you consider heavier tail environment. And this has been considered by Roberto Viveros in his PhD thesis. And I think he's in the audience today. Okay, so why did I talk about directed polymer? Well, because it's really the discrete version of the stochastic heat equation with multiplicative noise. So let me justify this claim. So now we are going to consider what I call the point-to-point partition function, which is simply, well, this renormalizing constant we had before. Okay, so the expectation of the Gibbs weight under the random walk measure, but this time we limit this expectation to the trajectories that end up at x. Okay, so it's kind of the contribution to the partition function of the trajectories that end up at x. And what we have is that this z and x satisfies some kind of discrete stochastic heat equation, which I write as follows. So if you look at the time differential, which is just the time increment of z, this is equal to 1 over 2d times the discrete Laplacian of z, which was introduced in Renato's talk, plus beta times eta n plus 1x times z bar nx, and z bar nx is simply the average of zn on all neighbors of x. So I won't give you the proof of this, but this really just amounts to using the Markov property for the simple random walk, and then you have to reposition the terms so that you get something like that. Okay, so now let's try to see what happens if I send if we send n to infinity and try to rescale things. So this thing will be replaced by a time derivative. My discrete Laplacian should be replaced by a continuous Laplacian. And okay, if I do this, if I tune a bit my parameters, I can even lose this 1 over 2d that I don't want and get just 1/2 of Laplacian in the limit. And for this, I just assume that this space average is not important. I will just get u in the limit, and my IID environment, what I should obtain in the limit is some noise if I tune beta with the right rate. Okay, so the formal limit of this should be the following equation, and you have to consider that this multiplication here is some Ito multiplication, because here eta is at okay, isn't the future immediately after n. So this is where the Ito multiplication comes in. Okay, and the initial condition that you have to consider if you want to have the analogy with directed polymer is really the Dirac mass at 0. So this is the motivation I'm having for my problems. I think this was also the motivation for Quentin studying this. And Karsten, well, he was coming from stochastic PD, so for him this was a motivation to study directed polymer, maybe. Okay, so in fact, this scaling limit, it's not only formal, and it does not only concern the partition function. So you can have a limit of the directed polymer measure, which will be a measure on Brownian trajectory, and the multiplicative, the stochastic equation will just give you the evolution of the point-to-point partition function for this continuum model. So this is the only thing I will say about the continuum polymer today, but you have to keep in mind that this is something you can do once you have studied the stochastic equation. And this is what Albert, Scanin, and Quastel have done in dimension 1 under the assumption of finite second moment. And in that case, when you rescale beta n, like n to the -1/4, basically you have, well, convergence of the point-to-point partition function to the solution of the equation I've given on the second slide. Well, in the case of polymer with that have environment that are in the domain of attraction of an alpha stable noise, in fact, you also have this convergence, but the equation you get in the limit is a stochastic heat equation with multiplicative alpha stable white noise. Okay, so this is what is alpha stable white noise. It's the analog of alpha. Well, it is to Gaussian white noise what alpha stable process is to Brownian motion. Okay, but I will come back to that just in a moment. Okay, so let's try to say a bit about something about the case of the equation with Gaussian white noise. So this is the equation we want to consider with Dirac at 0 initial condition. And what we will consider is really this weaker formulation, which is some kind of integral formulation. I don't ask you to check that this really corresponds. And in this integral formulation, this rho Tx is simply the heat kernel. So rho T is the Gaussian density, if you want, on RD. Okay, in dimension 1, in the case where Xi is Gaussian white noise, it has been shown by Walsh that this equation has a unique solution, and it has this form. So okay, basically to find the solution to this equation, what you can do is look at this weak formulation and replace U here by this whole expression. And each time you iterate this, you will create new terms on the right, and you just expect that this converges. So this is the expansion that you find. Okay, I'm not even expecting that you read all the formulas, but and here the integration is made on the simplex. The expectation with respect to time is made of the on the simplex of length c, and the expectation with respect to space is made on RD for every coordinate, and this rho Tx Sy, it's just the probability density that the Brownian motion go through all these space-time points. So it goes to yi for every si, and then it ends up at the point tx. Okay, so this is what happens for dimension 1, but if you want to do this in dimension 2 or higher, it actually doesn't work. So you can check maybe after this talk, that if you look at just the first term of this expansion, it's a Gaussian that has infinite variance. So already the first term of the expansion does not converge. And there has been some efforts to give an interpretation to the equation in dimension 2 and in dimension 3 or larger, but this is really a different game. So this is not what we are going to talk about today. And in any case, these interpretations, they are not really solution of the equation in the sense I've given before. Okay, so now I think we'll have 5 minutes to talk about our work. So what we have done is study the thing in the case of Lévy white noise, and found some optimal or near to optimal condition for the existence of the solution when the noise is not Gaussian but a Lévy white noise. And we have identified the asymptotic growth of the total mass of the solution. So this was the equivalent. Well, this is the equivalent of the free energy for the directed polymer. Okay, so let me try first to say what is Lévy white noise. So we start with a measure on 0 infinity, which gives finite mass to which has only finite mass on the interval 1 infinity, and for which z square is integrable on the interval 0, 1. And we consider a Poisson point process on a space with 3 coordinates. The first is time, the second is space, and the third will be used to model amplitude of jumps. And the intensity of this Poisson point process is just Lebesgue for the 2 first coordinates and lambda for the third one. And our Lévy white noise with intensity lambda, it will just be basically a measure that is a sum of Dirac mass at the space-time points, but multiplied by the amplitude, which is the third coordinate. And well, you cannot define it exactly like that because this sum might diverge and you might get a boring locally infinite measure. So you have to compensate for the small jumps if you want to have something non-trivial. And one way to do it is, well, you first truncate, make a truncator on amplitude in your definition. So you only consider atoms, well, points in your Poisson point process that have amplitude larger than A. And then sum these things and delete some drift, so some constant times Lebesgue measure, where this constant is simply the average on the interval A1 of Z against the measure lambda. And in order to obtain your Lévy white noise, what you just have to do is to make A tend to 0, and well, this thing converge to some non-trivial distribution in some functional space, or actually in some local Sobolev space of negative order, if you want. And the limit you obtain is Lévy spacetime white noise with intensity lambda. Well, of course, it's not the most general Lévy noise you can have. You could also have a Gaussian part. You could have negative jumps, but well, somehow we restrict it to this case to have well, for simplicity and also to keep the connection with the polymer, because if your solution is non-positive, then you don't have this connection with polymer. Okay. So now, what was our approach to existence of the solution of the stochastic equation with Lévy noise? So if the solution exists, it's kind of reasonable to assume that it should have the same expression as before. So this kind of chaos expansion, okay, where you have this multiple integral. The problem is that these stochastic integrals, well, they are not defined in L2 for sure. and it's not, even if you have another theory of stochastic integration, which is in LP, it's kind of difficult to show that these things are well defined directly. So our approach was to consider this thing with truncated noise and make A tends to 0 and hope that these things would converge. So this is the partition function we considered. And when you want to define this, actually, you have absolutely no problem with the definition, because if you take your truncated Levy noise, this is a locally finite signed measure. So the only thing you can, this thing is not a stochastic integral. It's really a measure theoretical integral. So in fact, when you look at this integral, you know, in my Lévy white noise, I have a Lebesgue part and I have a jump part. What you can do is first do all the integration with respect to Lebesgue part, at least formally. And if you do that, then you obtain a second expression for your partition function. You get first an exponential factor, which is exponential minus KAT, where KA is my previous drift term, and then you get something which is positive, where, well, it's the same thing as before, but except that you're only integrating with respect to the positive part of your noise. Okay, so this thing gives you something which is not apparent here, is that our partition function is positive, which is good if you want to consider it as a partition function of the statistical mechanics model. Okay, so in fact, okay, it's positive, but it could be infinite. So the first task we had was to prove, well, to find a condition on the noise so that this thing is finite. And we did that with Quentin and proved that the necessary and sufficient condition for Z to be finite is that log Z to the D/2 is integrable with respect to lambda. Okay, and I'm only considering well, the part on 1 infinity. So if this is satisfied, then your partition function is finite. If not, it's infinite, and it's the same condition for every x, t, and a, and beta. Okay. So from now on, we assume that this is true, and we look at the rest. We try to make a tend to 0. So because basically, when you lower the value of A, you're only adding additional noise information, and you're compensating it with the adequate drift. What you have is a time-reversed local martingale. It's only a local martingale because it could have infinite expectation, and therefore it converges when A goes to 0. So the important thing to determine is whether the limit is trivial or not, because if the limit is trivial, then it won't be a solution to the equation. So we want to find under which condition the limit is non-degenerate, and whether, when the limit is non-degenerate, whether it's a solution to the stochastic integration. Okay, so now I can present our first result, and basically what we proved is that, well, in dimension 1, you only need Z squared to be integrable to with respect to lambda. So it's the same condition for being able to define the noise. And in dimension 2 or more, we obtained a condition that Z to the 1 plus 2 over D times log Z should be integrable. Okay, and this time I'm looking at the small jump restriction of the noise. So if these conditions are satisfied, then we have a non-trivial limit, and this non-trivial limit is a solution of the stochastic equation with Dirac initial condition. And furthermore, under adequate integrability assumption for lambda, we even have LP convergence for our partition function. And the second thing we showed is that this condition we have on the noise is almost necessary. So in dimension 1 and 2, okay, so there are some typos here. you have to read equal infinity in each cases. But in dimension 1 and 2, if our previous condition is not satisfied, then the martingale, our local martingale converges to 0. And in dimension 3, we get almost the same thing, but except that you have to put a minus epsilon in the log. So there is a very narrow space of lambdas for which we are not able to say whether the martingale goes to 0. Okay, so this so the second set of results we have is basically about the growth of moments of our partition functions. And okay, whether it's up to you whether you want to ask questions about that, because I think I'm already over time. So thank you. No, I'm not over time. I'm not over time.
You're just in time. So
okay, yeah, so I should stop here.
Okay, yeah, so I should stop here. Yes, thank you, Hubert.